Swayam Prabha. Digital India. Educated India.
Welcome back. In Module 12, we will talk about different integrated systems and platforms. This is where we summarize the learnings that has been there throughout this particular course, and we will show you different examples or applications. Now, lecture 56 will continue with IoT systems. So, this is more of, we will show off different applications of IoT systems. Now that we know how to build some basics about, we know the basics about IoT systems, now we will look into different examples. So, the examples that we will cover in this particular lecture will be to demonstrate use of servo motors with Arduino. Then we will look into PIR motion sensors again with Arduino, then soil motion sensors and use of a solenoid, then Bluetooth communication with Arduino, and finally we will give you a demonstration of one of the projects from our lab, which is a bicycle smart lock. So, coming to the first project, we will demonstrate how a servo motor could be operated within Arduino. Now, servo motor is of course, it's an actuator, but it's a smart one. Why? Because we can determine to what angle that particular, this motor would rotate. So, that means we can have very specific control over the angle to which we can want to move certain things, right? For example, you want to move the arm of a robot in a certain direction, then that you can achieve. So, it's a smart actuator that rotates to a specific angle based on control signals from Arduino. So, this allows precision position control, which is essential in many automation systems such as traffic barriers, smart bins, robots, and so on. Now, what we require for this project, we require Arduino Uno or any other Arduino board. We require a servo motor, and I have already demonstrated how those look earlier. So, it could be SG90, which is very commonly available, or MG90S, which is a metal gear motor. So, it's almost looks similar, but it's a little bit different. Then you require jumper wires, you require USB cable, breadboard is optional, and the connections that has to be made is there are several wires coming out from the servo motor, and there will be a red wire which should be for VCC, and it will connect to the 5-volt line from Arduino. And then there will be a brown or a black wire which will be connected to ground in Arduino, and then there will be yellow or orange, which is the signal line, and that will be connected to digital pin 9 in this particular example. So, looking into the overall architecture, that means in this case the sensor is, we are going to use a limit switch as sensor, which will be the input. It will be a signal to start the motor or stop the motor. And then that means it is acting as a sensor in this case, and then there would be processing done through Arduino microcontroller. The actuator is the servo motor, which is delivering an output, and then serial monitor, you can say it will also sort of an output, and our data layer, which will help us to monitor what is happening with that servo motor. Now, we will demonstrate the code, of course, in the Arduino IDE. But before that, we will just discuss some of the key points that we have used in this particular code. That is, first we have to load the servo library. So, we will use a hash include statement, and then we will call the use the servo class from, of course, the servo library, and we have to declare an object first. That means that object would be my servo in this case. So, we declare an object of my servo of servo class, right? And then we can use the functions of the servo class. And servo would be connected to digital pin 9, limit switch would be connected to digital pin 7, and then there will be, we have to give comments like servo my servo dot attach, which will attach that servo to a certain pin. That is, we are specifying that Arduino should send the signal through pin number 9. So, whatever pin you have to specify. Then my servo dot write, where we will put the angle which will be between 0 to 180 degree, and we can specify to what angle the servo should rotate. And then looking into the limit switch, we can set it like when switch is not pressed, it is high, and when it is pressed, it would be low. And this press spelling is a little bit mistake. And when what we have to do, that we have to set this part, that is that the pin mode, when we are setting the pin and the mode, we have to say the mode would be input pull up. So that means we are setting the internal register, we are making it activated. Now what it will do is, so during when it is not pressed, it is actually shows it is high, and when it is pressed, it will be showing as it will be at a low value. So to do this, we have to set internally, we have to make the register activated, and because we are doing the opposite thing. And then serial, of course, we have to also send the information to the in the monitor. So we will use in this serial command, which is a built-in communication object, and we have to start the communication using a certain baud rate, which is nothing but the data speed, and that is usually set as 9600 as a default for serial communication. So this is the code that we have to put in Arduino. Now if you see over here that we are declaring that two servo pins and the switch pins first, and servo pin is set at 9 and switch pin is set at 7, and of course those are first declared as integer. And then in the void setup, we have to start with serial.begin, so that means we are initiating serial communication. Then my servo.attach, that means we are setting the pin of that servo, and then for that particular limit switch, we are also setting the pin mode, and we are putting the mode as input underscore pull up, and so that register is activated. And then we can say my servo.write 0, which actually will set the servo to the 0 value. That means the angle will be at the 0th value. And then we can also start, we can type in that, we can print in the monitor, that is serial.println system started. And then the actual loop part, that is which would be repeated, that is we are checking if digital read switch pin equal to low. That means if the limit switch is pressed, then my servo dot write would be 90. That means it will rotate the servo to an angle of 90 degree. And then serial.println, and it along with that it will print that the limit switch is pressed and servo at 90 degree. So that would get printed. If it is not else, then that means limit switch is released, and then my servo.write would be 0. That means again we will go back to the 0th position. That means as soon as I release the limit switch, the servo will go back to the 0th position, and you can say that and along with that we are printing that limit dot switch release servo at 0 degree, and then we are introducing a delay, and then again we can start. So that means this delay is nothing but to delay in the serial output, right? But because as soon as we are pressing, it will rotate. And we are now compiling, and after compiling we are actually we are first setting up as we have done earlier, that we are selecting the boards, and then we can compile it, and once we have compiled it, we can push it to the microcontroller. So these are the two steps that we will do. So here compo is 18, and we have selected UNO earlier, and then accordingly we can load the program into the microcontroller, and we are ready to see what happens after that. So now over here you can see that we have set up our system, and you can see that over here we are also showing the serial monitor what it is happening. So as soon as we press the limit switch, it will say that servo limit switch is pressed, or as soon as I release it, it will say limit switch is released, and it will show that what is the angle at when it is pressed, it will show 90. When it is released, it will show as 0. So and every 300 second it will keep on, if nothing is being happening, it will keep on printing the same thing again and again with a gap of 300 milliseconds, or 0.3 seconds, right? So this is how the servo program, servo demonstration project, we can do many things with that. We can have different sorts of systems where we have to change some rotate. So for example, you want to have a field of solar panels, right? And based on the angle of the sun, you want to keep on rotating the panel so that it faces the sun. So we can have a project like this where we have this larger motors, maybe which could where we can control the angle, and then we can keep on rotating that as per the direction of the sun, and that means we are optimizing the energy production. So that could be one application of this particular case. Then coming to another very important, very common as well as very important application of this sort of sensors that usually we may apply in many urban contexts, which is a PIR motion sensor. And this is a passive infrared sensor which identifies motion by sensing changes in the infrared radiation emitted by warm objects like such as a human body or so on. Now, this could help us in detecting occupancy, this can help us in detecting surveillance, and it can help automating security systems, right? Because the system is pretty reliable and it can detect anybody who is moving in. For example, suppose you want to understand how many people are there in a room. So I can set up this system in the door and I can count how many people are going in and how many people are going out. Maybe there are 2 doors, one for entry and exit, and we can determine how many people are there in the room. Accordingly, the AC has to be operated. Or it could be straight away for a case where we are just doing surveillance. That means if somebody unauthorized is entering during a time when a system is closed, somebody is breaking in, so we can detect that. Now, one of the very common modules that we use is this HC SR501 PR module, which is available. You can also get it from many from the internet or from local hardware store, IoT store, and where IoT this kind of sensors are available, and you can also test it on your own. So it's a low-cost, adjustable, energy-efficient device designed to detect movement in indoor and outdoor environments, and you can actually test it for different ranges and so on. So the sensor provides both a digital output. In general, it's a digital output, and it could be directly interfaced with Arduino or any microcontroller. And when motion is detected, the output signal becomes high. And when there is no motion, then it would be then it would be low. So then what we can see is there are different components. That is, we have the Arduino Uno board. Then there is a motion sensor. Then we can use the jumper wires. Then the breadboard, which is optional. If you want to, you can also use that. Then we are using LED indicators. If you are using the onboard LED, that is pin number 13, that is connected with pin number 13, that also we can use, or we can use an external LED with our 220 register, which is optional. So whichever way you want to go, you can you can set the system up. Now the connections would be like for the motion sensor, the VCC line will connect to the 5-volt line in Arduino. The ground will connect with ground in Arduino. The wire that is coming out will go to the digital input D2 in Arduino, and then there is the LED as well. If it is onboard LED, there is no extra wiring required, but if it is external LED, then we have to set it up as we have done earlier with an resistor. And so D13 pin should be connected with the 220 ohm resistor, and then it should connect to the LED anode, and the LED cathode should connect to the ground. So we will now look into the code over here, what we are writing. So we are of course we are trying to read what is the status of that particular this particular switch, that particular sensor. So PIR stat, it is basically we are reading the PIR output, and it's then digital read PIR pin is where we are reading the digital PIR output, and we are storing it in PIR stat. And then if that value is high, then motion is detected. If it is low, then there is no motion. So when motion is starts, we are checking if PIR stat equal to high and last state is low, because we are seeing that it is changing from low to high. That means somebody is coming in, right? So earlier it was low, now it is high. If it is high and high, then it's not that clear. And then motion detect, it will print the motion detected is motion is detected, and it can also turn on the LED. And when nobody is detected, then we can check if PIR stat is low and the last state was high, then motion is ended and the LED turns off. So over here you can see the pin modes. LED pin is set at 13, PIR pin is set at 2, PIR stat we are storing the value as 0 initially, then the last state we are storing it as low by default, and then void setup, we are setting the pin mode for LED pin, which is output, and then pin mode for PR pin, which is input, because because we are getting the value from the sensor, and then serial begin 9600 because we are using the serial monitor, and then void loop where we are first reading what is the input from coming from the PR pin, and we are storing it in PR stat, and if PR stat equal to high and last state is low, then we are digital writing the LED pin as high, and then that means the LED will glow, and we will print in the serial monitor motion is detected, hey, I have got you, and we are saying the last state, then we are initializing it to high. And else if PIR stat equal to low and last state is also high, then we will write digital write LED pin low, that means we will turn off the LED pin, and then the serial printing will be motion is ended or motion is not detected, something like that, and the last state we are converting it to low. So that means we are first when nothing is detected, we are making it low so that we can detect that somebody new has come. That's why we are using this last state, and we are constantly changing between high and low. So let's see how this particular thing looks. So over here you can see that means as soon as I bring my hand, I can detect motion is detected, hey, I got you, and then when the hand is not detected, then it is printing motion is ended. So we can continuously keep on doing that, and this is very sensitive, and we can actually tune to what distance and all we can do. So you can see that the control architecture is, of course, sensing layer is the motion sensor. It is sensing human presence. The edge processing layer is Arduino, and also actuation layer is, in this case, we could have a very speaker or a buzzer, but we are just turning on the LED. The communication layer is the serial message to the laptop or the monitor, and we can apply this particular kind of system for occupancy monitoring, intrusion detection, smart street light trigger, and different things. Like, or in a building also, if somebody is walking, then some lights will turn off. So those things could be done. But the other thing is we can do some alternative communication as well. That means if instead of sending the data to the serial monitor, I could send the data via Wi-Fi or GSM or LoRaWAN gateway to cloud dashboard or to mobile notifications, so that we can get a detection that somebody is breaking into my building. So that also could be done. The next project that we will look into is the soil moisture sensor with Arduino. So in this case, the soil moisture sensor actually estimates the total moisture content, and that happens by detecting the variations in the soil electrical conductivity. And when you pour more water in the soil, then it changes the conductivity of the soil, and that can be detected. So drier soil has got much higher resistance, so the values that we will record would be different from when the soil is wet. So it works by measuring the resistance between two metallic electrodes inserted into the soil. So you see, these are the two metallic electrodes that you can see in this particular image, and these are inserted into the soil, and then along with this particular electrodes there is something called a comparator, which is a sort of a device, or rather a circuit board, which which processes the signal that is coming from this particular electrodes, and it generates a digital output, because the signal that is generated here is analog, as we have discussed previously. This kind of probes will generate analog signals, and that has to be converted into a digital output, and it could be also based on some threshold value, that we can say that if the threshold is more, so either I can get the value in form of a range, or we can also get the value like high or low. If we can set a threshold of that for a certain value, we can say that it is either low or it is either high. So the probe, the moisture sensor, that means it has got two parts. One is, of course, the probe. It is this metal fork-shaped sensor inserted into the soil, and this senses the moisture level, and it measures the soil's electrical conductivity, and so it is converting the soil's moisture level to electrical signal. And wet soil has more water, so it is higher, it has got higher conductivity. That means there will be lower resistance between the electrodes. and dry soil has got less water, so it has got lower conductivity, so it will show higher resistance between the electrodes. So the comparator board or the control module, it is basically a small circuit attached, but it will have a small microcontroller within that as well, a small IC within that as well, and which processes the analog signal and compares it with threshold value and provides both the analog and a digital output. Now, it usually contains this particular IC, this LM393 comparator IC. So, it is a chip, of course, and it compares the voltage with the threshold values that has been set, and we can also adjust this particular threshold by changing a potentiometer, which is in a blue knob. You will see that within this circuit there is a rectangular box with a blue knob, and that could be changed to adjust the sensitivity threshold. That means when I should call it dry or when we should call it wet. And then we have power LEDs and signal LEDs are also there. That means when some signal is being sent, that LED actually glows. And then output pins, there are two output pins. One is for analog output, that is a continuous output, and the other is for digital output, that is on and off or high or low. So the analog output comes in form of 0 to 1023, which is this analog output is not the direct analog signal that is got. This is after conversion by the comparator. Then only we are getting it's a digital signal, but we are getting it in form of a analog output, which is the values would range from 0 to 1023. So this leads to precise moisture monitoring, that exactly we can see that what is the value. But again, it's a this value is not as per the actual that it's a digital representation of the levels of moisture that is in soil. And this is connected to Arduino A0 pin, and for example 300 most likely will be wet soil, whereas 800 would be most likely dry soil. And in case of digital output, which is comparator based, it either gives high 1 or low 0, and based on threshold set by the potentiometer. So over here you can see the program. So we are setting the sensor value initially as 0, and then we are storing the moisture reading from the sensor into this particular variable, and we are setting a limit of 500 ourselves. So this is not the limit set via potentiometer. We are just setting a variable limit of 500 to see which is high or which is low, and we can say that if it is greater than 500, then it is dry soil, and then if it is lesser than that, it is wet soil. And we are reading the sensor value with analog read from the we are storing the sensor value in the variable sensor value, and we are getting it using the function analog read, where we have to put in the sensor pin number, and analog read reads the analog voltage from sensor and converts it to digital value of between 0 to 1023. So we are getting both the analog signal as well as a digital signal, whichever you want to use, you can use. So in this case, we are using the analog signal. So INT server pin equal to A0. So we are setting up the analog sensor pin, INT sensor value equal to 0. That's the variable we discussed. Limit as 500, and in void setup, we are saying pin mode 13 is output. Serial begin 9600. So that is to start the serial communication. And in void loop, we are measuring the sensor, we are using analog read. We are measuring the value from the sensor pin, whatever is in this case sensor pin is A0, and we are storing it in sensor value. Then we are printing the moisture sensor value, where we are actually printing the value that is coming from that sensor using serial.print in sensor value. And if the sensor value is beyond that 500, which we have set as the limit, then we are turning on the LED, otherwise we are not turning on the LED, and between each of this we are putting a delay of 1000, right? So that between the sensing, that means each time it would be sensed, we are having a gap of 1000. So here you can see the setup that we have done. So we are using a breadboard, then you can see the Arduino Uno board, and then there is the comparator over here, and then the actual the probes are actually inserted into the soil over here. And to show you, so what we are doing is, First, I will show you the value. This is the setup, and you can see the sensor value is coming around 619, 618. That is when the soil is not dry, but it doesn't have that much moisture as well, right? So that is the initial value when we are measuring. So let's see. This is how the comparator looks like. You can see that that potentiometer with that turning knob and the LEDs also there, and then this is the the probe that is inserted into ground. And once I pour water into this, you can see the value of that sensor is coming down to 447 or 451, something like that. So you see that we can now measure the moisture content. So where is its application? We can apply this kind of sensors everywhere in urban areas. That means if we go for because there are a lot of landscaping and plants which are planted in urban areas, and we cannot do monitoring by putting human beings there. So sometimes if we have this kind of sensors, then we can monitor what is the moisture level, and we can turn on our irrigation system or a drip system so that automatic water is supplied to those particular locations. So this could be part of smart parks, green infrastructure, urban landscaping, climate resilient cities, and so on. Then we are showing you an example of use of a solenoid. Again, solenoid is something where we have already discussed what's a solenoid, and through Arduino we don't directly control a solenoid, but what we do is we connect Arduino to a relay switch, and through the relay switch we can control the solenoid. Now why it is that? Because the solenoid actually requires much higher power supply, right? And the relay switch is the device which can be turned on or off by signals from Arduino, and it turns on and off the electrical signal from a normal power line, and that is connected with the solenoid to supply power. So solenoid draws much higher current, as you can see over here, but the Arduino pin can only provide 20 to 40 milliamperes instead of 300 milliamperes to 2 amperes. So direct connection can damage the board, so that's why we require a relay switch. So also the voltage required by a solenoid is much higher, that is maybe 9 to 24 volts, whereas Arduino has got, the supply from Arduino comes around 5 volts, or it could be, if it's through a digital pin, then it is 3.3 volts. So that means we cannot directly connect Arduino to the solenoid. So what we do is we select a relay which will supply this amount of voltage, right, and it will be connected to a normal power line, and what we can do is we send a signal from Arduino to the relay switch to turn it on, right. So this is the sequence in which things are connected. We have Arduino which sends a signal to the relay switch, and the relay switch is connected with external power, and then only after that means external power is turned on, the solenoid actuation can happen. So relay is a electromechanical switch, we can say. It allows low power microcontrollers to control high powered devices. So if we want to have a smart control system for our lights in our room or some motors or something, then we can use relays in between Arduino and those high powered circuits, and it provides electrical isolation between Arduino and high power load. So this is very commonly used because, as you can see, one is a digital circuit, this microcontroller circuit that cannot directly connect to very normal electrical devices and all. So this is where a relay switch comes into play. So the relay connections are something like this, where there are two sides, the control sides, and then there is that's the low voltage side, and then there is the high voltage side, because that high voltage side is the actual connection with the normal power, whereas the low voltage side is connected with Arduino. So the Arduino's 5 volt pin is connected to the relay's VCC pin, VCC connection, and then Arduino's ground is connected with the relay's ground as well. And then we can turn the Arduino on and off, and accordingly we can set that pin high or low. Accordingly we can control the relay. And on the other side, the high powered side, switching side pins, there are 3 connections. One is COM, that is the main input power line that comes to that particular relay, and then there is NO and NC. NO is normally open and NC is normally closed. That means we keep the connection when we turn it open, then only the power will be supplied. If it is normally closed, then that means the relay is off and no power is supplied to the solenoid. So and at the same point of time, you can see over here we are demonstrating it. So we are using a limit switch as well to send power to that particular relay, and you can see over here that as soon as we do that, that means we can directly use through here we have used a limit switch just to complete the connection, and then what we can see over here is as soon we are turning it on, the solenoid is getting operated and so on. So this is how this is happening, and solenoid is also an inductive load. So when switched on and off, it generates a EMF pulse and which can damage the relay and Arduino. And so also we need to be careful about how the circuits needs to be, we need to give adequate protection to the circuits. So solenoids could be used in smart door locks, bicycle sharing docking locks, smart irrigation valves, running heavy pumps, and in many applications are there. So motors, solenoids, these are very common actuators that we use to control devices. Then we come to Bluetooth communication with Arduino. So it is not always, every code is written. We are controlling the actuation via code written in the microcontroller, but sometimes we can also introduce a, if we want to control those devices, then we can have our mobile applications which are loaded in our mobile phones, and through Bluetooth we can connect with those with the Arduino board, and we can send instructions, right? So this particular project will demonstrate you that. So Bluetooth modules use embedded radio chips to enable short-range wireless data communication between devices. So you can see this is one of the Bluetooth chips or Bluetooth module, you can say, right? So we call it, sometimes we call them the shield as well. So you can see that this is something which we have to connect to Arduino, and then only this Arduino will have the power to send or receive Bluetooth signals. And this helps us to pair devices to exchange data and typically form small range networks, otherwise known as piconets. And in this case, we have used this module which is Bluetooth low energy, and this particular Bluetooth low energy uses something called a GATT protocol. This is the protocol of communication, and this is usually results in energy efficient communication, means very low power, little amount of power is utilized. So in Arduino based IoT projects, we use this BLE module which is HM10, which is very common, and it allows wireless control and monitoring of sensors and actuators. So that means we are now introducing wireless control of the of sensors and actuators via the microcontroller, of course, but we can achieve that via sending Bluetooth signals. So all the Bluetooth speakers, Bluetooth mouse that you use works like this. So the components required would be Arduino Uno or some other similar boards, then HM10 BLE module or similar, LED which could be on board or connected to LED pin 13, or it could be a separate LED as well. Jumper wires, breadboard is optional. Then we require a smartphone with a BLE app so that it could send a signal and which could be help in pairing with this particular device. So the connections, looking into the connections, the Bluetooth shield, how it is connected with the Arduino pin, with the Arduino board, that means the VCC of this particular Bluetooth module would be connected to 5 volt of Arduino, or it could be 3.3 volt depending on which module you are using. Ground connects to ground, TXD connects to pin 2, and RXD connects to pin 3. Now TXD and RXD is used for communication. So in this case, Arduino, instead of connecting it to Arduino RX or Arduino TX as we have discussed earlier, so we are connected into pin 2 and pin 3. So these are known as software serials. That means we are converting the, that means we are instead of, because RX and TX may be already connected to a serial monitor or to some other device, so we can also define some of the digital pins of Arduino, and we can, using a software library, software serial, we can actually use them as for TX and RX, this kind of work. So, so instead of default hardware serial pins 0s and 1s, we can use, we can use these digital pins for, this kind of communication. So the communication flow is something like this, where the mobile app sends a command, then the Bluetooth module actually is, establishes that connection. Then Arduino is used for edge processing, that means it computes what has to be done, then it actually turns on an actuator which could be a LED on and off, and then feedback would be also via serial monitor where we can monitor what is happening. So, this is the code for this. So, what we are doing over here is we are using the software serial library, and so software serial BLE23, which actually says that pin 2 is equal to RX, which is receive data from BLE, and pin 3 would be TX, which would transmit data to BLE. And then serial begin 9600 one is for communication with the monitor in the laptop, and BLE.begin 9600 it also initializes the BLE module at a default baud rate for communication, which is again same 9600. And we can always print when the connection is established that serial monitor output HM10 BLE is ready, and then from there we can check if we send the information from the app, if that is received in that particular microcontroller or not, that we can check, and we can also print it. So, if available, so we can write code like if the data is available, then it checks if data is received from the mobile, and then and accordingly we can do something. And this is mostly like, because we are communicating via Bluetooth, it is mostly event driven communication. That means we are sending a signal, then only something will happen. And CAD CH is we are reading what is coming from BLE, and we are storing it in CH, which is a character type of variable, and and we can if that value is 1, we can turn on the LED. If it is something else, we will make it 0, and if it is 0, then we will turn off the LED. So, you can see over here in the code that includes software serial.h, we are including this library. Software serial BLE23, we are setting up the RX and TX connections, and then LED pin is set at 13, and then in the setup we are saying the LED pin is a output. It would be the pin mode is output. Then serial begin 9600, BLE begin 9600. So, we are setting the communications up, and then what we can do is then we can print that serial that BLE is ready, and then coming to void loop, if BLE is available, then we can read what data is coming from BLE, and then we can print received when we receive it, and then serial dot print in that particular value which we have received, and if then we can also, if the value is 1, then we will turn on the LED. If the value is not, then we will turn off the LED. So, that's a very simple program that we are doing, and once we are done with it, then we can upload the program, and once uploaded, then we can start the actual work, right. So, over here we are using an app called NRF Connect, which is a BLE app used to scan, pair, and communicate with BLE enabled Arduino devices. So, as soon as you download it from any Google Play Store or anywhere, you can scan. There are functions which allows you to scan for devices, and then you can connect. Over here you can see the different devices which are there and which are available within its range, and you can select the one which is your device, and then actually you can start communication. So, once you start connect, then we can establish communication, and then it can be used for real time data exchanges using the GATT services, and so using this we can control the microcontroller, and that means we are having a wireless interface here, and and then either it is sending 1 or 0, but we can also send something else, and accordingly the particular microcontroller will behave by turning the LED pin green, or turning it on or off. So, over here if you can see that we are sending a text value of 1, and when we are sending it, then received 1, LED is on, and this is how the connections has been done in the board, and the way we have already told you. So, this is the Arduino board, it is connected with this particular Bluetooth module, and then we are and as we are sending signals from the app, it is either turned on or turned off. Accordingly we can demonstrate wireless control. Finally, we will come to a product that we have developed in our lab. As you can see that this is a bicycle smart lock, which usually is imported from China and other countries. But this is a device which we have made in our lab, and we have a mobile, the application which we have also developed. Using this application, we can turn the particular lock on or off, or rather we can operate the lock. We do many things there, but to simplify, just to say that there is an actuator, there are motors inside this particular lock, which allows the arm of the lock to rotate and lock the cycle, and if required, it also opens when I send the open command. So if I say close command, it will close it. If I send open command, it will open it. So over here, I am opening the particular app, and I am scanning that particular code that is given there. That is how I establish which lock I am scanning. And once that is established, we can send a signal to this particular lock, which allows it to open. Then actually the bicycle ride starts because the lock is open. And when I say the bicycle ride is ended, so when I press it, you see the lock actually closes, right? So this is actuation that is happening, and this is a real life example of development of a IoT product that we have done in our lab. So these are some of the references that you can use. And to conclude, these demonstrations show how simple IoT components such as sensors, Arduino boards, wireless communication, and actuators can be integrated to create smart automated solutions that form the technological foundation of future data-driven and responsive urban planning systems. Thank you.